Go ahead.
So it's my great pleasure to introduce Lau and Dries to this talk at the MCA 2021. Lau graduated from Utrecht in 1978, but since arriving at the US in 1979, he's had most all of his career with positions in Stanford and UIUC, which he held for a very long time. And that makes him probably the most, or one of the most constant and influential figures of model theory in the Americas. He's not only worked in the US, but he's also given talks in many countries in North, Central, and South America. He has had PhD students from Colombia and Brazil. And Lau works in model theory. And I was reading in an interview recently that he chose model theory because he found it a way to use logic mathematics. And for me, that phrase may summarize much of Lau's work in our field. He, for example, improved Gromov's theorem on groups of polynomial growth using non-standard methods. And he's probably most famous because of long ago pioneer work in minimality. He somehow envisioned all these properties that eventually led to many applications in number theory that has recently come along. He will speak to us today about Hardy fields and Transseries, a work that, if I'm not wrong, it's been going on the making for 20 years, which has come around recently, has won him a prestigious CARP Prize of the Association of Symbolic Logic. And because of all of these, I think that I can't think of a better speaker to represent model theory at the Mathematical Congress of the Americas.
Right. Good. So, 20 years ago, we had a conjecture about Hardy fields, and we finally managed to prove that about a year ago, although we are still writing down all the details. So I want to start then with talking about Hardy fields and this conjecture, actually two conjectures, and then I will stop a few minutes and start with Transseries and talk about the connection between Hardy fields and Transseries. And of course, model theory is involved at several stages. So let's go to the next page. Okay, so here's some notation. So Hardy fields consist of germs of functions. So what functions? Well, for every R you have the CR, which is the ring of germs at plus infinity of R times continuously differentiable real valued functions on a half line from A to plus infinity. And here R can be any number from any natural number. And then if you take the intersection of all these rings, you get something that I write as C less than infinity. So, and that is a differential ring, because if you have a germ in such a in this intersection, then its derivative is naturally also defined and also in this intersection, right? And this has certain natural subrings, differential subrings, namely C infinity and C omega. C infinity consists of the germs of C infinity functions, and C omega consists of the germs of real analytic functions. And now what is a Hardy field? A Hardy field is simply, by definition, a differential subfield of C less than infinity. So here are some simple examples. Obviously, constant functions are differentiable indefinitely, and so you have Q and R as differential as Hardy fields, but you can also join the germ of the identity function, which we call X, so you get Rx, and of course you can exponentiate Rxe to the x, well, it's not, of course, you have to prove that this is actually a Hardy field, but actually in this case it's rather easy. And Rxe to the x log x is another example. And then also the gamma function, for example, the germ of the gamma function generates a Hardy field. Okay, and actually in this case, all the germs are analytic functions, are germs of analytic functions. Okay, so let's go to the next page.
Oh, so what would C omega be?
Excuse me?
What would C omega be? The ones that you can differentiate?
C omega, that is the consists of the germs of real analytic functions.
Great, thanks.
Okay, so there are lots of Hardy fields, and they are actually quite interesting objects algebraically and analytically, and also model theoretically, as we will see. So first of all, let H be a Hardy field. Then they are naturally ordered fields, because for a germ F, either you will have, since it's since also F inverse will be in H, that can only happen if Ft is greater than 0 eventually, or Ft equals 0 eventually, or Ft less than eventually. By the way, when I write F, and I talk about the germ, I often use the same letter for a representative of the germ, for a function that represents the germ. And so when I say Ft greater than 0 eventually, that refers to, of course, a function that represents the germ. But by saying eventually, it doesn't really depend on which representative you take. Right. And again, this is because if F is not 0, then it must have a multiplicative inverse, and that means that F cannot have arbitrarily large zeros. So they are naturally ordered fields. They are also naturally valued fields. And here we introduce a notation F dominated by G. Yeah, this symbol here, which means that for some positive constant C, the absolute value of Ft is less than or equal to this constant times the absolute value of G at T. Yeah, this is also often expressed in the big O notation. F is big O of G. But in valuation theoretic terms, this means that the valuation of F is greater than or equal to the valuation of G. For the natural valuation V on H, meaning it's the valuation whose valuation ring consists of all elements in the Hardy field which in absolute value are less than or equal to some natural number. And then finally, they are naturally also differential fields, and this speaks for itself because we define them as subfields of C less than omega, less than infinity, which are closed under the derivation on that differential ring. So, and again, there are three possible cases. The derivative is less than 0, which means that F is eventually strictly decreasing, and F prime can be 0, which means F is eventually constant when you talk when you take a representative of this germ, and you can have also that F is eventually strictly increasing. Okay, let's go to page 5. Right. So now, yeah, I should say Hardy fields were introduced formally by Bourbaki, but they go back really, and Bourbaki did this to systematize certain older results by Hardy and Dubois-Reymond from the 19th century, Hardy from the early 20th century. and the term Hardy field comes from Bourbaki. And they also proved in their appendix, well, they actually introduced it in an appendix in their book on real analysis, and they proved a few basic facts about Hardy fields. Like, for example, that if you have an element of a Hardy field little h, then you can take e to the power h, which then generates a bigger Hardy field. And also you can always adjoin an antiderivative. If you have an element in a Hardy field, you can take an integral from, you can take a germ g whose derivative is h, and that will also generate a Hardy field. And then actually a more basic result in some sense, which Bourbaki did not do in their book, but was later shown by Abraham Robinson and Rosenlicht and other people, that you can always take the real closure of a Hardy field as a Hardy field, right? So H has a unique algebraic Hardy field extension, which is real closed. Okay, and so in particular, this last thing has as consequences that you can always adjoin arbitrary real numbers to your Hardy field. And you can always adjoin the germ of the identity function, which we call x. And also, of course, if you have a positive element in your Hardy field, then you can adjoin the log of h, because the log of h, if you take the derivative, you get h prime over h, which already is in capital H. Right, so in particular, this means that maximal Hardy fields must contain all the real numbers. They must be real closed by the first fact stated here, and they must be closed under exponentiation and integration, because you can always do it, right. And of course, also closed under taking logarithms. Right, and of course, by Jordan, there always exist maximum Hardy fields. And actually, one of the things that we now know is that there are very many maximal Hardy fields, namely 2 to the continuum many, right? A Hardy field is a subset of C less than infinity. Oh, my connection is again unstable. I hope
No,
that,
we can.
Can you still hear me?
Yes, we can hear you well. Well, I can hear you.
Yes, we can,
Okay.
we can hear you.
Fortunately, I hope this problem disappeared. So, right, since C less than infinity has cardinality of the continuum, and a Hardy field is a subset of it, that can be at most 2 to the continuum many Hardy fields. And in fact, there are 2 to the continuum many maximal Hardy fields. Not that that is a very big deal, but I just wanted, yeah, good. Let's go to the next page. So now I can actually introduce a conjecture that we made at the beginning of our joint work some more than 20 years ago. And that is that you can, that you have an intermediate value property for differential polynomials. Yeah, so up till fairly recently, the extension theory of Hardy field was pretty primitive. Basically, the extension results that I mentioned on the previous slide, that was what we knew and not much more. So this intermediate value property would add an enormous amount of further information to that. And it's the natural thing. If you have 2 germs, f and g, in a Hardy field capital H, and f is less than g, and you have a differential polynomial, that means a polynomial over h in the variables y, y prime, y double prime, etc. And pf is less than 0, less than pg, then you want an intermediate y in some bigger Hardy field, perhaps, where p vanishes, right? So we want py is 0 for some y in some Hardy field extension of capital H with f less than y less than g. So So you will see this is a very nice analog with the real numbers, where you have, of course, the intermediate value property for ordinary polynomials. But here we want it for differential polynomials, which is, of course, fairly ambitious. You can also state this in terms of maximal Hardy fields, namely maximal Hardy fields have the intermediate value property for differential polynomials. In other words, you don't have to go to an extension anymore because you are in the maximal Hardy fields. So what we now know is that this conjecture, we already, since a few years, we already knew that this conjecture would imply that all maximal Hardy fields are elementarily equivalent. Yeah, they all have the same elementary first order theory. We didn't know that at the beginning of our joint work, but I'll come back to that. But since a few years, we did know that it would imply that. And a few years ago, we also came up with a roadmap of establishing this intermediate value property. And a year ago, we finished the proof, basically. But it's still a lot of work to put this in a readable form. I mean, the proof is really long, more than 150 pages. So we are still working on that. But this conjecture is not a conjecture anymore. It's a proof. It's a theorem, though not yet published. Okay, so I hope it's clear what this conjecture says. And let's go to the next page then. Right. And then there is a conjecture which, after the first conjecture, well, which you came up with a bit later, namely that maximal Hardy fields are eta 1 sets. And that uses Hausdorff terminology about totally ordered sets. But what this really means is that if you have a Hardy field and countable sets capital A and capital B in capital H, with capital A less than capital B, this means every element of A is less than every element of capital B, then we want a Y in some bigger Hardy field that is bigger than everything in A and less than everything in B, right? So, so that's also a natural conjecture, and in some sense the two conjectures together give a picture of maximal Hardy fields. And in fact, if you assume the continuum hypothesis, the two conjectures together imply that all maximal Hardy fields, are in fact isomorphic, assuming this second conjecture. The first conjecture is proved. The second conjecture, not quite. It's almost there, I think. If we still have we still need to do a bit of work, but we almost proved the second conjecture as well. And right. So I think I will stop here for a few minutes as required before I turn to Transseries. And I can, if you have any questions so far, let me know.
Okay. Are there any questions from the audience? No. I have a question. So,
yes.
It feels that when you have a pseudo-Cauchy sequence having a pseudo limit, one should be able to find this point that is like a pseudo supremum of A. So that the hard part from getting to what you have to the second conjecture is to, given a countable set A, having a pseudo Cauchy sequence that actually sort of gets to the supremum,
Well,
or am I completely wrong on the strategy?
Well, also, you see, body fields means that you have that the value group you seem to have disappeared.
I don't know if it's my connection or yeah, I took off my camera because I was not listening very well.
Oh,
but
okay.
maybe because of the time issues, maybe we can talk about this later.
Yeah, it's not just gaps in the. You also have to deal with gaps in the value group, countable gaps in the value group, which cannot be described in terms of pseudo-Cauchy sequences in the Hardy fields. So, and these are these other gaps come from the value group are quite different. You have to use totally different techniques for it. Yeah.
Okay,
so let's go to Transseries now.
Let's continue. Yes.
Okay. So since this is really about the connection, so originally what our work was not about Hardy fields, but rather about Transseries, and it's only later, the last 6-7 years, that we have tried to make the connection between these two topics. So what is a Transseries? It's a series, a typical example is written here. It's a series where you can use not just powers, but also exponentiation and logarithms. And so this is a typical example of a Transseries. And you think of x as being positive infinite, so as a variable that goes to infinity in the real line. X is bigger than every real number. And here the monomials we call, in this series, we call transmonomials. And they are range from left to right in decreasing order with real coefficients. And they also involve exp and log. Oh yeah, this is some stuff that I eliminated in my version of the slides. So yeah, so what else can I say? The field T of Transseries are basically obtained by starting with ordinary Laurent series in 1 over x and closing off under exponentiation and taking logarithms and reasonable infinite sums. And the precise construction of these Transseries is a bit delicate. It's fully done in our book, but I will just assume that you will have a feeling for it from the example. One thing I will mention is that given a Transseries, there is a finite bound on the nesting of exp and log. For example, if you have 1 over x plus 1 over e to the x plus 1 over e to the x plus 1 over etc., that's not in our field T of Transseries, because the exponentiation here has arbitrary deep nesting, and that's not allowed. And likewise, the second series that I wrote down here involves log x, log log x, log 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 x, etc., and that is also not allowed. These series do make sense in a certain spherically complete extension of T, but not in T itself. Okay, let's go to the next page. Right, so here are a few basic properties of the field T of Transseries. It's a closed ordered field extension of R. And you can always differentiate the Transseries term by term. And when you do that, you can have a lot of cancellation. Like in this example, if you differentiate it term by term, all you are left with is e to the x over x. And you also see here that e to the x over x on the right-hand side makes perfect sense as a function. As a on the left-hand side, you get something that is a divergent series, but there are summation procedures by which one can actually sum such. Anyway, gives you a derivation. The real numbers, and you can also show that every transseries derivative. See the analogy with the fields. Okay, let's go to the next page. So, like with Hardy fields, we introduce evaluation by means of these symbols. F is dominated by G if and only if the absolute value of F is less than or equal to a real constant, positive real constant times the absolute value of G. And then we have the equivalent relation. F is asymptotically equivalent to G, and F is strictly dominated by G. And here are typical example. E to the minus x is strictly dominated by x to the minus 10, strictly dominated by 1, strictly dominated by log x, etc. Right? And just like in Hardy field, you have the following general rule that if you have a Transseries which is bigger than every real number in the ordering on the Transseries, then its derivative is greater than 0. And another thing that is very important is that you can differentiate and integrate the dominance relation. F is dominated by G if and only if F prime is dominated by G prime. But there is one condition that you should pay attention to, namely that this only holds if you assume that F and G are not asymptotically equivalent to 1. Right. So let's, yeah, good. Thanks for we go to the next page. Let me see what is the time yeah, I'm still.
So you have about 20 minutes left.
20 minutes, yeah, okay. Right, I think this is doable. I'm slide 11, so now for model theoretic purposes, we are going to consider T as a valued ordered differential field. And that means we introduce the language where you have symbols for the constant 0 and 1, and addition, subtraction, multiplication, and a symbol for the derivation, for the ordering, and also for the dominance relation. And actually, it's convenient to do that in a somewhat more general setting where you have any ordered field K, differential field K, with a constant field C. And then that already gives you a dominance relation, namely defined in the same way as for the Transseries, namely F is dominated by G if and only if F in absolute value is less than or equal to a positive constant from the constant field times the absolute value of G. Right. And so that means that you can, any order differential field has automatically a valuation on it coming from order. An L structure for this language L that I introduced. And also introduce valuation ring, the corresponding valuation ring for this relation, namely simply the elements in K which are dominated by 1. The bounded elements is also the convex field of the constant field in the big field K. And then you have this, in this evaluation ring, you have a maximal ideal of infinitesimal consisting of the elements in K which are strictly dominated by 1.
Now is gone again.
I know.
I pause the recording again till Lau reappear. Go ahead, please.
I don't see this. I don't see the screen yet.
Okay.
Ah, yes. Okay, we are back. Let's go to the next page. Can you go to the next page? Ah, yeah, here we are. Right. So we introduced these ordered differential fields as valued ordered differential fields, and but the only ones that we are interested in for our story is the so-called H fields, which are kind of abstract versions of Hardy fields, and they are the ordered differential fields which share certain elementary properties with Hardy fields, namely that if f is bigger than all constants, then its derivative is positive, and secondly, the valuation, the bounded elements are exactly the constant plus the infinitesimal elements. Yeah, big O is constants plus little o. So Hardy fields that contain all real numbers are H fields, and differential subfields of T that contain R are also H fields. And T itself is, of course, therefore an H field, but T has further basic elementary properties that that we have to talk about. Namely, its derivation is small, and it is also Liouville closed. So small simply means that an infinitesimal element has also an infinitesimal derivative. Yeah, if f is strictly dominated by 1, then f prime is strictly dominated by 1. And Liouville closed means that you can solve all first order linear differential equations, plus it's still closed. So Liouville closed means real closed, and for every f in k, there are gh in non-zero gh in k, such that g prime is f and h prime over h is f. Yeah, so the logarithmic derivative of h is f. Every element is a primitive and a logarithmic primitive, if you like. Okay, let's go to the. So these are elementary first order properties. And then one big scheme is the intermediate value scheme. Namely, we say that an H field K has the intermediate value property if for every differential polynomial capital P and all f less than g with pf less than 0 less than pg, there is a y in between f and h. Oh, that should be even g instead of f and h, so that py is 0. And then we can state the following fundamental theorem, which we proved, which is one of the main results in our book from a few years ago. Namely, that the elementary theory of T is completely determined or axiomatized by saying that it's an H field with small derivations. So these are all simple axioms. Liouville closed, right? Real closed plus every linear differential equation of order 1 has a solution. And then this satisfying this intermediate value scheme, which is an infinite list of axioms. Right, and in fact, it much more is true. I mean, this theory is model complete. And so here I'm using a little bit of model theoretic terminology, this theory is model complete and is in fact the model companion of the theory of H fields with small derivation. Yeah, I didn't want to get into that on my slides, but I may as well say it.
Lau, you're muted.
Thanks. Can you hear me?
Yes.
Are you now? Okay, good.
Yes, we can.
Yeah, I should say the theorem is not in this form in our book because we only IVP, this intermediate value property, is a bit of an afterthought, and I mention it here for expository reasons, and because it explains why the first conjecture on maximal Hardy fields implies that all maximal Hardy fields are elementarily equivalent, because they satisfy maximal Hardy fields if this first conjecture is true, as we have proved now, they do satisfy the intermediate value property, and they also have these other satisfy these other two properties. So they will be elementarily equivalent to T. Right. Yeah. So we can go to the we can go to the next page. Yeah. So to explain this situation is we proved the theorem in the book with IVP replaced by two more fundamental conditions, namely being omega free and Newtonian, but unfortunately they are rather complicated and technical, but they are quite fundamental and actually make sense in a wider context, not just in the context of H fields. And then we only later noticed, maybe 2 years ago, that they are for H field equivalent, for real closed H field equivalent to IVP. Right. Yeah. Well, I say here a bit more about omega free. It's basically a condition on solutions of homogeneous second order linear differential equations. Liouville closed is about first order linear differential equation, not necessarily homogeneous. And this is about omega free is something about homogeneous second order linear differential equation. And it's a very robust property and is in particular preserved and passing to any densely algebraic H field extension. And a few years ago, we established that every Hardy field extends to an omega free Hardy field. So that is part of our first conjecture that maximal Hardy satisfy all the axioms. And already a few years ago, maybe 5 years ago, we already knew that. That's already a fair amount of work to do.
I think we lost him again.
Yeah, Lau, you're muted again.
He's back. There you go.
Right. Let's go to the next page. Oh, there is seems. Can you go to the next page?
Yeah, there is.
Newton. Yeah, this is a post that I probably interpolated. That is condition mentioned here, and you can think of it as a powerful version of Angelianity for differential fields, differential Angelianity. So let's go to the next page. So our conjecture then amounts to showing that maximal Hardy fields are Newtonian, because we already showed they are omega free, and the other properties, Liouville closed, are old. So I want to give some ideas about how to prove our first conjecture, or how we proved our first conjecture. So let's say we have a Liouville closed omega-free Hardy field that is not yet Newtonian, and we want to show that it. So then it's enough to show that it can always be extended to a strictly larger Hardy field, right? Because if it were maximal, it would have to be Newtonian if we can show this. So from our book, we know that the condition on H given element H hat, an infinitesimal element H hat, which lies in some immediate H field extension. Not a Hardy field extension necessarily, but an H field extension, an abstract H field extension H hat of H, where satisfying P8 hat is 0, where Py is a differential polynomial of order r greater than or equal to 1. Let me see.
He's back.
I see. I ask him to unmute.
Yeah, unmute again. Now you should unmute.
I have unmuted now.
Yeah, we can hear you.
But I don't yet
see the
don't yet see the slide.
Yeah. Okay.
Ah. Okay. Right. So if we assume that it's not Newtonian, then we get this H hat in an immediate H field extension which satisfies the differential polynomial equation over H and so this is a kind of minimal counterexample to being not Newtonian, right? There is no differential polynomial in H of smaller complexity. And I'm not going to define that, but there's a natural complexity on differential polynomials. Which have an immediate H field extension of H. So, in other words, P8 hat is a minimal witness to H not being Newtonian. Okay, let's go to the next page. Do you hear me?
Yes.
Yes.
Can you go to the next page? Oh, okay, we are already in the next page. Okay, now this minimality one can exploit in certain ways, and it's also preserved in the various natural operations. And operations is reposed with element in H, little h. And various tricks and transformations of this kind enable us to arrange that capital P is this differential polynomial is quasi-linear in a very strong sense, meaning that its degree 1 part is of order R and strongly dominates the rest of P. Now the conditions, the actual conditions are very technical, and I'm not going to explain this, but there is a sort of general term that people use, namely quasi-linear, which means that the degree 1 part is somehow dominating. And we also can arrange that this linear part, when you view it as a linear differential operator, is very close to a linear differential operator that splits completely when you work over the algebraic closure of H, right? Since H is real closed, we can, when you join I, it will become algebraically closed. Now, this is very complicated. I mean, it takes about 100 pages to arrange this. And on the other hand, it works in a very general setting of H fields, not just for Hardy fields, and that has certain other consequences. But once I've done that, the rest is more analytic in flavor. So let's go to the next page. Right. So then we can, using all that, this quasi-linearity, there is, I think this is a fairly general technique to solve the frequency. Everything in a sort of Banach space context. So to construct a solution to this differential equation and show that it generates a Hardy field extension, isomorphic to H, yeah, H A hat should be, I get Y hat, or F, what I used Y hat there on the previous page, so that's another error, that typo. Anyway, we consider a certain Banach space of CR functions, complex valued actually, whose derivatives up to order R are bounded, and with some rather complicated norm, not the norm you would expect. It's a sort of weighted by in different orders of derivatives. And anyway, we can obtain then such a solution as a germ of a fixed point of a certain contractive operator on a closed ball centered in this Banach space. And the right Banach space is a little bit complicated. And we also have to do everything in this complex setting. And then, because then we can exploit the fact that this linear differential operator associated to P splits completely. And yeah, so then we can construct a left inverse to this linear differential operator, and that enables us to this fixed point is actually generates a Hardy field. I mean, it's a priori a complex valued function, and well, in fact, you can take its real part. So when you take the fixed point, we actually take the real part of the fixed point, and that is what has to generate a Hardy field, and that is also a lot of work. So let's go to the page 18. Right, and now this is basically the last slide, so I think I'm actually in time. So here we have to use a fact about complex valued functions over Hardy fields, and this amounts to a certain analytic fact about exponential sums over Hardy fields, and that might be of independent interest. So here it is. You have a Hardy field, and you have germs in this Hardy field which are linearly independent over this valuation ring of the Hardy field. Yeah, so they are, if you mod out by OH, their cosets will be R linearly independent. And then whenever you take any n functions in or germs in the algebraic closure, if this linear combination f1t e to the power I v1t dot 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 f1 plus f1 nt e to the power I v nt goes to 0, as t goes to infinity, that can only happen because the f's themselves go to 0. Right, and that involves certain results about equidistribution mod 1 and almost periodic functions. So that's a totally different area of analysis, which also comes in at this point. Okay, so you can go now to the next slide, because that's the last one, and that's where I thank you for your attention. And I hope I'm not... Okay, that's it. Thank you.
Well, thank you very much. It was, and thank all the audience for powering through these difficulties and everything. And it's an amazing,
yeah,
amazing results. And thanks, Nir. You saved us in many occasions.
Yeah, you saved us. Sorry for the instability, but I was still able to get through it.
Yeah.
Sharing?
Yes. So I don't know if we actually have time for one or two questions. I don't know if any of you have some questions. No. I have one. When you did the book result with omega-free and Newtonian, did you already expected that these two were the keys to proving the intermediate value property?
Yeah, well, we sort of, how shall I say, we did in some sense already know that it implied the intermediate value property. And we were so focused on this omega-free and Newtonianity properties that we didn't pay too much attention to the intermediate value property. And then at some point, I thought, let's find out whether we can go in the opposite direction from the intermediate value property to omega-free plus Newtonian. And well, I mean, this is actually what I submitted for the paper for this meeting. There we show the equivalence of these intermediate value property and with omega-free plus Newtonian for Liouville closed 8 field. So it was sort of in the back of our mind, but we didn't pay too much attention because, well, we were too focused on these other two things. And it's mainly an expository thing, right? I mean, intermediate value property you can immediately explain to anyone, while omega-free and Newtonian, it's more fundamental in some sense, but it's
Well, we lost him again. I think I can stop the recording at least.
I hope.
Oh, here.
I'm back.
Yes.
But I think did I answer your question?
Yes, you did. You did. Thank you very much. Any other questions? No? Okay, then, Guillermo, I think we can stop the recording.
Yep.
I have one. When you did the book result with omega-free and Newtonian, did you already expected that these two were the keys to proving the intermediate value property?
Yeah, well, we sort of, how shall I say, we did in some sense already know that it implied the intermediate value property. And we were so focused on this omega-free and Newtonianity properties that we didn't pay too much attention to the intermediate value property. And then at some point, I thought, let's find out whether we can go in the opposite direction from the intermediate value property to omega-free plus Newtonian. And well, I mean, this is actually what I submitted for the paper for this meeting. There we show the equivalence of these intermediate value property and with omega-free plus Newtonian for Liouville closed 8 field. So it was sort of in the back of our mind, but we didn't pay too much attention because, well, we were too focused on these other two things. And it's mainly an expository thing, right? I mean, intermediate value property you can immediately explain to anyone, while omega-free and Newtonian, it's more fundamental in some sense, but it's
Well, we lost him again. I think I can stop the recording at least.
I hope.
Oh, here.